To understand what makes a molecule polar, we will start off by taking a look at an oxygen atom located on the left. Within the first electron shell of an oxygen atom, there are 2 electrons. Within the second shell, there are 2, 4, 5, 6 electrons. This gives us a total of 8 electrons, and electrons are negatively charged particles. Just like every other atom within the periodic table, oxygen has just as many positively charged protons within its nucleus as it has negatively charged electrons within its shells, and that comes out to 8 protons. What's important for the moment is the fact that oxygen has 6 electrons within its second shell, but it would actually like to have 8. So now we can take a look at 2 hydrogen atoms. Each hydrogen atom has 1 electron within their first shell, and that must mean each has 1 proton within their nucleus. But what's important for the moment is each hydrogen atom would actually like to have 2 electrons within that first shell. So what you have is 1 oxygen atom with 6 electrons in its second shell when it would like to have 8. And you have 2 hydrogen atoms, each with 1 electron within their first shell when each would like to have 2. So, through electron sharing, also known as covalent bonding, we can get a molecule of water. Water consists of an oxygen atom sharing electrons with 2 hydrogen atoms. And what you will notice is now each hydrogen atom has 2 electrons within their first shell, which is what each wanted. And the oxygen atom now has 8 electrons within its first shell, which is what it wanted. So you have created a stable molecule of water. However, the oxygen atom is more electronegative than the hydrogen atoms are. So the oxygen atom pulls electrons towards itself, and the electrons spend more time towards the oxygen atom than the hydrogen atoms. Another way of saying this is the electrons are more unevenly distributed towards the oxygen side of the water molecule than the hydrogen side of the water molecule. And since electrons have a negative charge to them and they spend more time towards the oxygen side of the water molecule, the oxygen side has a slight negative charge to it. Thanks to the proton within each hydrogen, the hydrogen side of the water molecule now has a slight positive charge to it. Because of this slight negative and slight positive charge to each side of the water molecule, it is referred to as polar. Any molecule that shares this characteristic is called polar. Ammonia is another example of a polar molecule. It consists of a nitrogen atom sharing electrons with 3 hydrogen atoms. And the nitrogen atom is more electronegative than the hydrogen atoms. Thus, the electrons spend more time around the nitrogen atom compared to the hydrogen atoms. This makes the nitrogen side of ammonia slightly negative, while the hydrogen side is slightly positive. And this means that ammonia is a polar molecule. Polar molecules are called hydrophilic. By definition, hydrophilic means water-loving. What this means in real terms is that polar molecules can bind with water molecules because water molecules are also polar. And this also means that those molecules can dissolve in water. To get a better understanding of this, let's take a look at how water molecules bind with one another. In this image, there are 3 water molecules. And what's going to happen is the negative oxygen side of one water molecule will bind with the positive hydrogen side of another water molecule. This is referred to as a hydrogen bond. Hydrogen bonding is how water molecules bind with and coexist with one another. So now let's take ammonia, which is a polar molecule that we would call hydrophilic. What will happen is if we put ammonia in water, the negative nitrogen side of the ammonia molecule will bind with the positive hydrogen side of a water molecule. Also said, ammonia will form hydrogen bonds with water molecules. And what this means is ammonia will dissolve in water. This is why ammonia and other polar molecules are called hydrophilic. The difference between ions and polar molecules is often misunderstood. To understand what makes something an ion, we can start off by taking a look at the sodium atom located on the left. Sodium, just like all other atoms within the periodic table, starts with the same number of negatively charged electrons within its shells as it has positively charged protons within its nucleus. To begin with, it has 11 negatively charged electrons and 11 positively charged protons. Importantly, though, it only has one electron within its third shell, and that means the sodium atom will not hold on to this one electron very strongly. Now we can look at a chlorine atom, which starts with 17 negatively charged electrons within its shells and 17 positively charged protons within its nucleus. Importantly, it has 7 electrons within its third shell, and it would really like to have 8. So if you allow a sodium atom and chlorine atom to interact with one another, what will happen is the chlorine atom will take the electron from the sodium atom. So now the sodium atom got rid of the one electron it wasn't holding on to very strongly in its third shell, and the chlorine atom, which is now called chloride, got an 8th electron within its third shell, which is what it wanted. What you now have are two ions, a sodium ion and chloride ion. Sodium is an ion now because it lost one of its negatively charged electrons, meaning that it now has more positively charged protons within its nucleus. It has 11 positively charged protons within its nucleus and 10 negatively charged electrons within its shells. This means it now has a positive charge. Chloride, on the other hand, gained an electron. It now has 18 negatively charged electrons within its shells and 17 positively charged protons within its nucleus. This means it has more negatively charged electrons than positively charged protons, giving it a negative charge. Any atom or molecule that gains or loses an electron will be referred to as an ion. This is very different than a molecule that's polar. What makes polar molecules and ions similar is the fact that they're both hydrophilic. To repeat from the past, hydrophilic means water-loving. This must imply that ions can bind with and thus dissolve in water. So let's start off by taking a look at a sodium ion. We know that sodium ions have a positive charge because they have more protons than electrons. So if you take sodium ions and put them into water, since they have a positive charge, they can bind with the negatively charged oxygen side of water molecules, which, as we know, are polar. And this means that sodium ions can dissolve in water. And now we can take a look at chloride ions. We know chloride ions have a negative charge because they have more electrons than protons. So if we put chloride ions into water, since they have a negative charge, they can bind with the positively charged hydrogen side of water molecules. This means chloride ions will dissolve in water. So sodium ions, chloride ions, and all other ions are hydrophilic. They can bind with and dissolve in water. So now let's take a look at a different type of molecule. Here we start off with one carbon atom in the center. You may notice that the carbon atom has 4 electrons within its second shell, and it would like to have 8. Surrounding the carbon atom, I have 4 hydrogen atoms. You already know that each hydrogen atom has 1 electron within their first shell, and each would like to have 2. So now you have a carbon atom which has 4 electrons within its second shell when it would like to have 8, and 4 hydrogen atoms, each with 1 electron within their first shell when each would actually like to have 2. What will happen is through electron sharing or covalent bonding, the carbon atom will come together with the 4 hydrogen atoms and form what is known as a hydrocarbon. If you look, now you will see that each hydrogen atom has 2 electrons within their first shell, which is what each wanted. And the carbon atom has 8 electrons within its second shell, which is what it wanted. Importantly, this hydrocarbon has a very symmetrical shape. What that means is the electrons are very nicely and evenly distributed throughout the molecule, and they can't spend more time towards one side of the molecule versus another. And this means one side of the molecule is not going to have a negative charge and the other side have a positive charge. Instead, the molecule is largely neutral, and this is referred to as being nonpolar. Nonpolar molecules are said to be hydrophobic, which means water-hating. What this actually means is molecules that cannot bind with water and thus cannot dissolve in water. So for example, if we took the hydrocarbon on the left, which is nonpolar, and tried to put it with the water molecule on the right, which is polar, they would repel one another. This is because they have no means of binding with one another. The nonpolar hydrocarbon does not have a positive and negative side, and the polar water molecule does have a negative and positive side. So they cannot bind with one another. This means that hydrocarbons and other nonpolar molecules cannot dissolve in water and are thus hydrophobic. A simple experiment that can be done to demonstrate this involves taking a glass and filling it with water, and then taking some cooking oil and putting the cooking oil into the glass as well. What will happen is the water and the cooking oil will completely separate from one another. This is because cooking oil is made up of fat, also known as lipids. Lipids are made up of hydrocarbons. We know that hydrocarbons are nonpolar. So what you're doing when you take cooking oil and put it into water is you're actually taking a whole bunch of nonpolar hydrocarbons and putting them with a whole bunch of polar water molecules. They end up entirely repelling one another and 2 separate layers are created. So let's conclude with a short experiment where we take water and put ammonia, sodium ions, chloride ions, and hydrocarbons into the water. We know that ammonia is polar. It has a negative and a positive side to it. That means it can bind with water molecules and dissolve in water molecules. That is why we call ammonia and other polar molecules hydrophilic. We know that sodium ions have a positive charge and chloride ions have a negative charge. This means sodium ions and chloride ions can bind with water and dissolve in it. This is why sodium and chloride ions, as well as all other ions, are referred to as hydrophilic. And lastly, we have hydrocarbons that we put into the water, which we know are nonpolar. There is no positive and negative side to nonpolar molecules. That means the hydrocarbons will not be able to bind with the polar water molecules. They will repel one another. This is why hydrocarbons and other nonpolar molecules are referred to as hydrophobic.